Hi everyone, here are your notes. Oh, now I don't know where my face ended up. All right, he'll still hit present. Nope. Okay, maybe I'll put my face over here. Okay, so let's get into your chapter 23 notes. So now we're going to start talking about inference with means. So we talked about William Gossett in class and how he discovered the issues that were occurring using the normal model for really small sample sizes. So what does this mean? Instead of using the normal model for these problems, we are going to start using the student's T models. So these curves are going to be more spread out and they have more area in the tail. So you can see here in the diagram, we have our normal distribution in the middle, and the T distribution is definitely flatter and your tails are fatter, right? And we're going to be using S to estimate sigma. There is a greater uncertainty and variability within that. So the student's T models, there's hundreds and hundreds of different T models that we could possibly use. To identify which model to use, we use degrees of freedom. For one sample means, our degrees of freedom is equal to n minus 1. So you can see over there on the side, we have our normal model, right? Which if our degrees of freedom was infinity, like it would keep bumping up our T model closer and closer to being the normal model. So as our degrees of freedoms gets higher, the higher that peak's going to come and the more closer it's going to get to the normal model. So here's a quick video explaining degrees of freedom.
Degrees of freedom is a concept that you'll find cropping up repeatedly in statistics you have to do for your degree. For example, you'll usually have to quote a value for the degrees of freedom when you present the results of statistical tests. Also, calculating certain kinds of estimates, like the standard deviation of a sample, involves degrees of freedom. But calculating others, like the mean, doesn't. Why? And is this the same degrees of freedom concept as the ones you quote alongside a statistical test? Well, the first thing to say is, understanding actually what degrees of freedom mean isn't desperately important for this module. You'll need to write the degrees of freedom down in your assessment, but you don't need to understand exactly what it is. Degrees of freedom is a tricky concept. Many good biologists can't tell you exactly what it is. This video is just for context, so that you have a chance to understand this number that you're being asked to write down for your assessment. I'll give you its definition first, but this won't mean much until I start to give you some examples. Whenever you calculate something, anything like a mean, standard deviation or test statistic, the degrees of freedom is how many independent pieces of information you needed in order to make that calculation. Now that sounds like I'm talking about the sample size, but it's not the same as your sample size, as we're about to see. The degrees of freedom are going to be different depending on what particular calculation it is you're making. And, here's the really important bit, they will also be different depending on what you already have to know before you make the calculation. The simplest example of degrees of freedom is a coin toss. A coin toss has 1 degree of freedom. If you toss a coin, you know you can only get heads or tails. So you know, in advance of tossing the coin, that the total number of possible outcomes is 2. If you get heads, you automatically know that you haven't got tails. I don't have to ask you, but did you also get tails? Given that we already know there are 2 possible outcomes, then one piece of information, whether we got heads, allows us to work out also whether we got tails. This is a system with 1 degree of freedom. Now let's say I while away some time by tossing a coin 100 times. You want to know how many heads and tails I got. What you know in advance here is how many times I tossed the coin, and also that there are only 2 possible outcomes. Again, only 1 piece of information is now needed to work everything out. If you know the number of heads I got, you automatically know the number of tails I got. So you only need to ask me one thing. So even though we have 100 coin tosses, given that we also know that there were only 2 outcomes, we still have only 1 degree of freedom, because only one piece of information is needed to work out everything we want to know. In contrast, here is a system with 2 degrees of freedom. You and I are having a phone conversation, and you tell me that you're looking at a traffic light. I ask you over the phone, what colour is the light? Now I know in advance that there are 3 possible outcomes, red, amber, or green. Or you tell me, well, it isn't amber. Now that leaves me with 2 choices, so I still don't know what colour it is. So I say, stop toying with me, what colour is it? And you tell me, well, it's not green either. And now I know the light must be red. Given that we know there were 3 possible outcomes, 2 pieces of information were needed to work out everything we needed to know. This is a system with 2 degrees of freedom. Another case with 2 degrees of freedom is the 3 cup and ball trick. You're trying to work out where the ball is. You know in advance that the ball can only be in one of 3 cups. You turn over the yellow one and it isn't in there, but you still don't know where the ball is. You turn over the red one and it's not there either. Now you don't have to turn over the blue cup. It must be in there because it wasn't in the other 2. 3 possible outcomes, 2 required pieces of information, 2 degrees of freedom. So those examples are all for cases where the data are categories, like red, green, heads or tails. In these cases, the degrees of freedom is usually the number of categories minus 1. Now, let's widen our imagination a bit and see how this applies to things we can measure. When you calculate the mean of a sample, you don't know anything beforehand, and the value of the mean that you get will depend on each and every one of the values in your sample. In other words, if any one of those values varies, even slightly, you'll get a different value from your mean. But, as we're about to see, this isn't the case for standard deviation. As we learnt in our lecture, calculating standard deviation involves subtracting the mean from each value. So, in order to calculate the standard deviation, you first have to know the mean. Otherwise, you can't work out how much each value deviates from that mean. Without first knowing the mean, standard deviation doesn't make sense. This is a bit like knowing the number of times you tossed a coin, without which the number of heads you got makes no sense. But, when you come to think about it, if you already know the mean, this means automatically that you don't need all of the data values in your sample to be able to calculate the standard deviation. Why is this? Well, for example, if you have 3 numbers and you know their mean is 5, if you then find out that the first 2 numbers are 4 and 5, then the last value has to be 6. It cannot vary. So once you know the mean, you only need to know 2 of those numbers, and then you then automatically know the last number, a bit like not needing to turn over the last cup to know where the ball is. So because you already know the mean, the standard deviation doesn't depend on each and every one of the values in your sample. The value of the standard deviation only depends on n minus 1 of the values. Because you've already worked out the mean, the nth value in your sample effectively doesn't contribute to the standard deviation. Thus, the number of pieces of information that go into calculating the standard deviation, that is, the degrees of freedom, is n minus 1. This is important.
Okay, so we're going to pause it there. Don't need to go any further. So there is your degrees of video. So when do we use the T model instead of the normal model? Well, when we don't know the population standard deviation, which really happens most of the time. It's very hard to actually know a whole entire population and know its standard deviation. So we're most likely using the T model most of the time. So when we don't know the population standard deviation and when we're using the sample standard deviation to estimate what we think the population standard deviation is. Okay, so again, this is pretty much always for means problems, because when in real life, are we just going to happen to know the standard deviation of the population? Rarely. Other facts about the t-distribution that are good to know. The t-distributions have more area in the tails compared to the z-distribution. They're going to be more spread out. And since there's more area, that gives us a bit more probability. As your degrees of freedom increase, the t models look more and more like the normal model, otherwise known as the z-distribution. In fact, a t model with infinite degrees of freedom is exactly normal. And we went through this website earlier on where you can change the slider. Where is the slider? Here it is. So here's my degrees of freedom at 1. If I move it to degrees of freedom of 6, we're getting closer and closer. So the blue is the t distribution. Notice over here your probabilities, right? So here would be your p-value under the t distribution. Here would be the p-value at the normal model. If I keep going, right, I keep getting closer and closer to my p-values being the same. And as I kept getting higher and higher, let's say we get to 30. Why is 30? 31, why is that a good cutoff point, right? Because what does the central limit tell us? Is that if our sample size is large enough, then we can be approximately normal, right? So the higher we get, and then if we keep going all the way up to infinity, in this case it's 100, we keep getting closer and closer and closer, right? Okay, so we went through that. Oop, come back, here we are. Okay, so confidence interval formula differences. So if we know our population standard deviation, so if we know sigma, what do we normally do? We would do x bar plus or minus our z-crit times our standard deviation of the population divided by the square root of n. Remember, that's how we found standard deviation with our sampling distributions of means. Do you remember doing that? So that is our standard error for there. If we only know S, our sample standard deviation, which is pretty much always, then what are we going to do? Well, we are going to do our x bar plus or minus, and then here we end up doing what's called the t-crit, right? Our t critical value times our standard error of the sample, which would be S over the square root of n. So what's changing? We're changing the model from the z distribution to the t distribution. And instead of using sigma, which is the population standard deviation, we're going to be using S, which is our sample standard deviation. And remember, x bar is specific to our sample mean, right? So in both, we have the sample mean, but here we're going to be using our sample standard deviation when using the t distribution. So let's go ahead and practice finding critical values. Let me get my calculator popped up here. So we want to find the critical value of t for a 98% confidence with degrees of freedom of 10. So when we go to use our calculator, again, so 98% would be in the middle. So let me go ahead and get this up here while it's going. So we need to think about the tails, just like when we were doing our z critical value. So if 98% is in the middle, that leaves me with 1% here, 1% here. And if you guys remember, we would do an inverse norm of 0.01, and it would get me this z value, and then I would just make it positive. Well, since in a t distribution, we have multiple models depending on our degrees of freedom. So in this one, we're doing degrees of freedom of 10. So when we go to second vars, instead of number 3, we're going to go down to number 4, inverse t, and then it's going to ask for our area, which still is 1% to the left, right? Because 98, 2, and then cut in half. Yeah. Our degrees of freedom, when I say it was 10, and then I would hit enter. And then it's going to give me the negative version, but my t critical value would be positive 2.76. For n equaling 20, so I'm going to go back in and do that again. So second vars, number 4, 0.01. Now if n is 20, then my degrees of freedom is n minus 1, so 19 gets me my t critical value to be 2.539. Might be a good set of numbers to go with. Okay, so make sure you can do that on your calculator. If you have a TI-83, this is the one thing your TI-83 does not have, and we're gonna have to figure out how to, well, you're gonna have to figure out how to program it in. I can find you and send you a video on how to do that. So if that is the case for you, you'll have to let me know, because you have to make a program for your calculator to find the inverse T. It is possible, but a little bit of work. All right, so our conditions for a one sample t interval t-test for means is, again, we need a random sample, the 10% condition for independence between trials. This still applies, but honestly, for a means problem, it generally can be assumed because sample sizes are going to be small. That's why we're using the t-model. Thus, it's not as important to check it. So I'll let you off the hook if you leave it out, but when in doubt, put it in there, I guess. So just stick to our normals, random 10%, random 10%. Just stick to the process and keep it consistent is what I would do. And then for our third one, we need our nearly normal condition. So if you guys remember back when we were talking about sampling distributions, we need to make sure that our sample size is large enough. So in proportions, we use our success failure, right? And then how do we check? And so if it's large enough, then we know that it's nearly normal, right? So when we're talking about sample means, how do we know whether it's nearly normal? Well, our options are as follows. The best one is it says your sample distribution is normal or something like that. It says the word normal out there for you, and that you're like, great, it told me it was normal. Perfect. So the nearly normal condition is checked. That's the easiest. We need to either then make sure, if it doesn't tell us that it's normal, then we want to have a large enough sample size that our central limit theorem kicks in. So where's our cutoff? 30. So our sample size is greater than 30. So the central limit theorem tells us that the sampling distribution will be roughly normal. Or if we don't have a large enough sample size, and we have a whole bunch of data, then we would have to actually put that data into our calculator and either look at the histogram, look at a dot plot, or probability plot's probably the easiest. I don't know if you guys remember doing probability plots. I feel like we did it a little bit because that's the one where you just kind of make your line, right? Your probability plot, you just kind of like this, and then it gives you a whole bunch of dots like this. And if that probability plot is roughly linear, then we know that our distribution is roughly normal. So if we're not told, if our sample size is not large enough, then we actually have to make an image of the sample and then say, hey, our sample does look roughly normal-ish, right? We don't want to see outliers. Nothing's going to be perfectly normal. Nothing will be perfectly linear when you make those probability plots. So I don't know if you guys really quickly remember how to do those. Do I have a list in here in my stats? Yeah, they're pretty ugly, but we'll go with it. That's probably for, I don't know what that's from. But if you go to second y equals for your stat plot, and you go in there, your probability plot is that last one over there. It looks like a line. And then you would pick a list. I don't know, we'll go L1. And then do zoom 9. Oops, I got some cubic stuff happening in here. That looks pretty linear. It's very linear, huh? So I would recreate a quick sketch of that, and then I would say the probability plot is roughly linear, so the sampling distribution is roughly normal, right? Something like that. Okay, so coming back, let's go ahead and move into our first example here. So it says, students investigating the packaging of a potato chips pack purchased 6 bags of Lay's potato chips marked with a net weight of 28.3 grams. They carefully weighed the contents of each bag, recording the following weights in grams. We want to create a 95% confidence interval to estimate the mean net weight of Lay's potato chips. So right away when I start seeing data like that, I'm going to pull out my calculator and I'm going to clear all my lists. Let me clear these out. I didn't want me to clear them out. I thought there was a way to clear them out, but I guess not. Clear lists. Maybe I had to pick the ones. That's okay. I'll just go in here and clear them myself. All right, so clear, clear. So I only have one set of data, so I'm going to put everything in list one. So let's go ahead and type in these weights. So 2.29.3, 28.2. You probably want to do this along with me so that you know that you can do it. If I could type this in, 28.2, 29.1, 28.7, 28.9, and what's my last one? 28.5, 28.5. Okay, so what we can do to save ourselves some time, if I go back to stats, go over to test, and I want to run we don't have anything that says one sample t-interval, so it's my students like to call it the tinterval. Number 8 is our tinterval. That's our one sample t-interval. We inputted data. If I was given the stats, then I would go over here to stats, and then it would request me to just type in the sample mean, a sample standard deviation, how many things were there. But we have data in here, so I have everything under list 1. The frequency is 1. There's nothing crazy happening there, and we're doing a 95%, so 0.95 is my confidence level. And then I'm going to hit enter. So notice what my calculator gives me. It gives me the mean and the standard deviation right away. I could have gotten that by running a one variable stats, but it just takes a little bit more time. So I'm going to leave that there. I'm going to kind of just do my work here. So how do we do a confidence interval? We panic. Sorry, I'm just trying to give myself some like blank space here. All right, so what is my P in this case? My P, or not my P, my mu, right, is parameter. In this case, we're mu. So mu represents the true mean weight of all Lay's bags. Okay, so there's my P, my parameter. My parameter in this case is mu. My conditions for the A, assumptions and conditions, is we're going to, do we have a random sample? Let's tell us we had a random sample. Nope. Okay, so random, we weren't stated. So because it wasn't stated, we're going to assume these 6 bags are representative of all Lay's potato chip bags. 10%, I would definitely say 6 is less than 10% than all chips, of all bags of chips. And then our normality, so our nearly normal, normality, large enough. So 6 is definitely not large enough for the central limit theorem to get into play, right? And we're not told that the distribution off the bat is normal. So now what we're going to have to do, I'm going to undo this for a second, is I'm going to have to do a probability plot. So I'm going to go in here and stat plot. I'm going to keep the list 1 there. So I think we're good. So now I'm going to do a zoom 9. And there's my probability plot. So that looks pretty linear, I would say. So for normality, I would make a quick sketch. 1, 2, 3, 4, 5, 6. I don't know how even that was. And I would say something like the probability plot is roughly normal. So I'm running out of space. The distribution is normal, or the sampling distribution, I guess I should have said, is normal. Sorry, that's really down there. Okay. So again, probability plots are probably the easiest. I could have made a histogram of that, but then I might have to play around with the bin widths on my calculator. So just do a probability plot, because that's really easy to sketch, because you're just making a dot plot that looks, or a scatter plot that looks straight. And then you just say the probability plot is roughly normal, so the sampling distribution is roughly normal, right? Okay, so then where do we go from there? With conditions met. Get rid rid of this stuff. All right, so with conditions met, we can use the T model, and always attach your degrees of freedoms here, because T models, there's an infinite number of models. Degrees of freedom would be 6 minus 1, so 5, and create a 1 sample T interval with 95% confidence. Okay. I don't think I spelled confidence right, but that's okay. All right, so now our calculator did the work for us. So now we got to do the actual interval. We named the model, named the test, or named the interval. So let's just quickly write it out. So it's x bar plus or minus t crit times standard deviation of the sample over n. So let's go ahead and fill in some blanks. So we've got 28.78 plus or minus. We have to do some calculator work to get that t crit, but I'm going to leave that blank for now. And then my standard deviation of the sample was 4.02 over the square root of 6. And then I'm going to actually jot down what the interval was. So 28.361 to 29.205. Okay, so now I got to do some work to find that t-crit value. So I'm going to undo this for now. So we're going to do second vars, inverse t. For 95, my lower tail would be 2.5, so 0.205. And I don't know why this all of a sudden is not giving me everything. Degrees of freedom, we said, was 5. I don't know why it changed the mode. So 2.57. So let's bring this back. So 2.57, I'm going to put in for my t-crit. All right, so there's my interval. So now I just have to conclude in context. So we are 95% confident that the true mean weight of Lay's potato chip bags is between, and where are we between? 28.361 and 29.205 grams. And this is used all the time. You know, there's lawsuits that actually end up happening because maybe their weight that they are putting on their package isn't right. Maybe they're shortchanging people some potato chips, right? I'm sure people wouldn't care if they were over. If this confidence interval was higher, that wouldn't be very good, right? Or that would be okay. People were like, oh, I don't mind getting more potato chips, but people would be pretty angry if this confidence interval was lower than what the actual bag was saying it should be, right? Because you're paying for it, you should want all the potato chips you can get. Okay, so there was a confidence interval that we just ran through. All right, so now what we're going to get into is some backwards movement. So finding necessary sample size. So let's suppose you want to estimate the mean amount of money spent on prom by Marshwood High School students with 90% confidence. Tough subject right now for you guys. You plan on taking a sample of students who attended last year's prom, and based on data from the previous years, you have a good idea that the standard deviation of the money spent is $45. If you want the margin of error to be no more than $10, how many students should you sample? Okay, so what are we doing here? We need it to be a 90% confidence interval, right? So we don't know what the sample size is, right? So we don't know what our degrees of freedom would be, so we wouldn't really be able to find the t-crit. But what we could do is we know that the t distribution and the z distribution are pretty close the higher my n gets. So I can use my normal model to first come up with what I have an idea my sample size should be, and then use that sample size to come up with my degrees of freedom to get a t-crit value to then solve for my actual sample size. So we're kind of solving for n twice using two different models is what's going to be happening. So for 90%, our z-crit value using your calculator is 1.645, right? And we know that margin of error for sampling distributions would be, so our margin of error would be equal to our z-crit times sigma over the square root of n. So we want our margin of error to be no more than 10, so $10. Okay, so 10 is equal to 1.645 times, what was this, 45, I think is what we said, 45 over the square root of n. So when you do some math out, you end up getting n is equal to 54.8, which always round up, right, to account for that error, because we want to be n. So 55 students would be a good idea of our n. Now, we could then take that and make that our degrees of freedom. So my degrees of freedom would be 54. And then what we can do is we can then find our t-crit value. Okay, so let me get my calculator out here. T-crit value, so inverse t, we're still at 95, right? Was it 90 or 90%? So that would be 5%, 0.05. Degrees of freedom, we said was 54. So my t-crit for that is 1.67. 1.67. So we could do our 10 is equal to 1.67. I probably should have did some more decimal places there. Times my 45 over the square root of n. And then using our calculator, we're going to do 10 divided by 1.67. And then we're going to do 45 divided by that. And then squaring that. I need to like grab a calculator. Trying to use my phone. All right, 10 divided by 1.67. Actually, I'm going to do 10 divided by my inverse t, 0.0554. Okay, do that. And then we're going to do 45, because I would multiply that out, 45 divided by that. 45 divided by that. 45 divided by that. I should be doing this on the calculator so you're watching me. And then squaring that gets us 56.7. So not too big of a difference. So here we get 56.7. So about 57 is what we should be sampling. So remember, the higher the better. So if we just use the normal model, we would be doing 55. But if we were using the T model, we'd be doing 57. So is it that big of a difference? Probably not. Is it safer using the 57 over the 55? Yeah, I would say so. Okay. All right, so now let's go to the next slide here. So now you want to estimate the mean SAT score for AP Statistics students at Marshwood with a 98% confidence interval. The standard deviation of scores for all Marshwood students is thought to be about 195 points. If you want the margin of error to be no more than 25, what is the desired sample size? So we're going to do the same thing. So we have 25 is equal to, so 98, it's going to get us a z-crit of 2.326. Times 195 over the square root of n. So that gets us 329.2, which I'm going to round up to 330. And then that would get me my degrees of freedom. Now, because this is so large, I don't think this is going to be that big of a difference. So 329 would be my degrees of freedom. My t-crit value on that would be, so 98, right? 98, so 0.01. 329 gets me a z-crit value of 2.3377. So now when I do 25 is equal to 195. Oops, I forgot my 2.377 times 195 over the square root of n. So let me just show you what I'm doing on my calculator. So on my calculator, I am doing, oops, save it. I'm doing, oh, now I just lost it. Ah, we lost it. Where are we at? 195 divided by, so then what you can do is second vars for 0.01239, or nope, 329. Had a point of dyslexia there. Paste, right? So it's going to do that. Or no, it's going to, I needed 25. What am I talking about? 25, my margin of error divided by that. And I'm going to do 195 divided by that answer. And I'm going to square that answer. And I get 332. Right? So I think I lost my writing that I had before. So n, so when we did that, 25 is equal to 2.377, I don't know what it was, 195 over the square root of n. You end up getting n is equal to 322. Is that what it was? 25 divided by, got too many things happening here, huh? 195 divided by that squared. Yeah, 332, not 22, which would round up to 333. So 333 students would be who we would need to interview or sample. Okay, so find it twice. If you're doing a multiple choice question, go with the bigger one. If they don't have the bigger one, then go with the smallest one. Okay, so now this gets us into hypothesis testing, so doing this with phantoms. So we know that we have our different z-score formulas. So to find our z-score, when we know the standard deviation of the whole entire population, we do our mean, sample mean, minus the mean of the whole population, divided by sigma over the square root of n. But if we don't know the sample or the population standard deviation, we need to use the sample, then we're going to use our t-score, and we always put a little subscript of our degrees of freedom down there. It's going to be equal to x bar minus mu all over our sample standard deviation over the square root of n. Okay, so always attach that degrees of freedom as a subscript when you're finding your degrees of freedom. Okay, so here we want to estimate and approximate p-values for the following. So again, I'm going to make this smaller so we can get over here. Okay, so p-values. So if I just was finding p-values, I would go to second vars, and you should see instead of normal PDF and normal CDF, in 5 and 6 we had TCDF. That's what we would be doing. So we have a t-score, so I'm going from negative 999 to my t-score of 1.55, and my degrees of freedom is given to me as 10. So my p-value is 0.9239. For part B, I'm going to hit second vars, go down to number 6. We're going from negative 9999 to negative 2.32. I'm assuming that first one was left tail. Degrees of freedom would be 19 if my sample size is 20. And that gets me 0.0158. Okay, so that's how you would find the area underneath the curve, which is your p-value, given a t-score. Okay. All right, so back here, this is our last one. Okay, so we're going to finish up our example. We're going to phantom test or significance test, talking about some rabbits. It's Easter season. So we've got this rare breed of pastel-colored, high-jumping rabbits. And we're thinking that they have a mean jumping distance of about 35 feet. A scientist is concerned that recent environmental changes may have altered these rabbits' jumping ability. So we want to do a 10% significance test to decide if The jumping ability of these rabbits has increased, and then interpret our p-value. Now I forgot to type in the actual data here, so you might have to add it in yourself. I forget if I have it on the notes or not. It's 25, so we took 11 rabbits and we measured how far they can jump. So we got 25, 30, 52, 45, 42, 36, 39, 12, he didn't do very good, 50, 59, and 73. Okay, so then what we can do is we can go in and type that stuff into our calculator. But before we do that, I'm going to get the basics things written down here. So for our phantoms, right, phantoms, P is my parameter. In this case, my parameter is mu. Mu would be the true mean jumping distance of this breed of rabbit. My ho and my ha. So my ho would be mu is equal to 35. So nothing's changed. It is what we expect it to be. My ha would be that there's an increase. So it's greater than 35. All right, so let's check our conditions. Random, it's not stated, so we're going to have to write something like assume the sample is representative of all rabbits of this breed, right? I'm going to come up here. 10%, I would say 11 is less than 10% of all rabbits of this breed. Rabbits of this breed. Now I have to check normality. Unfortunately, my sample size is not larger than 30. Then I could just say, oh, the CLT says that it is. And we're not told that it is normal. So we have to now go to our calculator and input our data. So I'm going to clear out my list 1. And I'm going to type in my weight, or my distances. So 25, oops, I just put a 2. 25, 30, what else we had? 52, 45, 42, 36, 39, 12, 50, 59, 73. And then I'm going to run a stat. Let's do our stat plot. It's all good. Zoom 9. I'd say it's roughly linear, right? So then we would say something like, do this, a little bit of an outlier there, a little bit of curve. Okay, there's my plots. The probability plot is roughly linear. So the sampling distribution is roughly normal, right? Okay, so we got all that. Now I'm going to erase all that. We got our conditions. Now we need a name. So with conditions met, we're going to use the T model. Degrees of freedom is 11 minus 1, so 10. And proceed with a 1 sample T test with not with, alpha is equal to 10%, so 0.10. Okay, so there's our N. So phantoms, P-H-A-N, check, 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 check. Now we got to do our T, our test statistic. So this is where we got to find our T-score, right? So on my model, we have 35 in the middle. My X bar, so using my calculator, I can come up with all of this information. So I'm going to go and run my stat test. In this case, you would Do we have a one sample? I don't think we have a one sample. I think we would just run a t-test. Yeah, so we're just going to run a t-test. We put in our data. Do I have my, nope, data. So our mu naught is 35. We put our data in list 1, and we're doing a greater than, so that's good. I'm going to calculate this. All right, so there's all the information we need. So my x bar is 41.09. My standard deviation of the sample is 18.9. And then our p-value is the 0.155. Yeah. All right, so if we put those in, I'm not going to remember that. Let's see if I can remember this. So my standard deviation is 18.9, 41.099. All right, 41.099. Standard deviation is 18.9-ish, right? So then my t-score, with degrees of freedom being 10, is going to be equal to 41.099 minus 35 over 18.9 or whatever it was over the square root of 11. And my t-score was, oh, it's 41.09. No, that's what I put. T-score was 1.069. 1.069. My p-value is going to be equal to probability that my x bar is, so 35, so we were at 41, right? And we were doing the shading, is greater than 41.099, which is equal to the probability that my t-score, degrees of freedom of 10, exceeds 1.069, which was equal to 0.155. 0.155. All right, so now we got to make a conclusion, make a decision, and then make a conclusion. So I would say with a high p-value of 0.155, which is greater than 0.10, we fail to reject the null hypothesis. There is not sufficient evidence to suggest the jumping ability, and just kind of restate the question. The jumping ability of these rabbits has increased. Has increased. All right, hopefully your handwriting's better than mine. The last thing we had to do there was interpret the p-value. So let's do a quick interpretation. So if we said something like, so remember, if the hoe is true, so what was our hoe? So if the mean jumping distance really was 35 feet, there is a 0.11 or what was it? 0.55 probability of, if that p-value was different than what it was, make sure you put the right p-value, of choosing a random sample of rabbits with a mean jumping distance of 41.09 feet or more, because we were doing the right tail. Okay, so there's your p-value interpretation. All right, that concludes your notes.